Alright, hi y'all. Uh, this next video is going to be going over this waveguide design. So, yeah, I think a good way to start here, let me think about how, I want to start this. Maybe reading the problem might be a good way, right? So design the dimensions A and B of an air-filled rectangular waveguide that is to be used for transmission of EM power at 12 gigahertz. So we know frequency is at 12 gigahertz. The frequency should be at the middle of the operating frequency band. So what we'll notice is in controls and systems, or not controls, circuits and systems, and in signals and systems, you learn about bandwidth. And, in electronics you also do, but more so in controls or circuits and signals. What bandwidth is, you have, some band pass filter, or some sort of, any filter. You have this Bodie plot, and the bandwidth is the this frequency that is wanted, that is passed through a filter or has the highest gain, right? So this can be like the transfer function, h of s, and this is in omega. And what we notice is our frequency is, or our bandwidth is the about here and here, maybe like our 3 dB frequencies. This is our bandwidth here. And it's frequently, modeled by a range of frequencies in hertz. So our bandwidth, our cutoff frequency, our low cutoff frequency, and our high cutoff frequency, that's our bandwidth. So our bandwidth here is equal to F high minus F low. Whenever you do in circuits and systems, you have to make these Butterworth filters or any type of band pass or band reject filter. They ask you to solve for the bandwidth frequency, and this is how you would do it. You would find the 3 dB frequency. This is the 3 dB frequency here, and the 3 dB frequency here, and you find the bandwidth, which is the high 3 dB frequency minus the low 3 dB frequency. This is we want to make sure this stays constant based on our parameters for A and B. So that's kind of just a little bit of a back story here. And of course, for this problem here, this would be 12 gigahertz. In between, we want to make sure that stays constant and it stays stable. Anyways, that was kind of just talking about cutoff frequencies, because it can come up in this type of problem. It says this frequency would be at the middle of the operating frequency band, which is the band over which only the TE10 mode can propagate. Choose the height B of the waveguide so it can carry max power without sacrificing the bandwidth of the operating frequency band. Okay, so for this question, what we should know is in the TE10 mode, to choose B so that it doesn't sacrifice the bandwidth and carries max power, we need to choose B equal to A over 2. So whatever we get for A, we want to make sure it is twice A, or half of A, sorry. So what is A though? Well, the way we get A is we set the frequency equal to 1.5, the cutoff frequency, which again was that picture before. Cutoff frequency goes from right to left, so it'll be either 1.5 greater, which is your 3 dB frequency, or 1.5 less than our operating frequency band we want. So anyways, that's besides the point. Now what we can say is this is 1.5 times the speed of light in the dielectric divided by 2 times A. And A is what we're trying to find. Well, the speed of light in the dielectric is, there is no dielectric. It's just 3 times 10 to the 8th. So it's the speed of light. Now A, or more like 1 over A, is equal to, let's see, F divided by 1.5 times 2, and we have CD, which is 3 times 10 to the 8th. What is F though? Well, F is literally what we have right here. So F is 12 times 10 to the 9, 12 gigahertz. So we have 12 times 10 to the 9 times 2. But we want A, not 1 over A. So what we should do is we should do 1 over A to the power of negative 1, or flip, A. So we can, I'll leave that here actually. 1A negative 1 is equal to A is equal to 12 times 10 to the 9 times 2 divided by 1.5 times 3 times 10 to the 8th. And this is all to the power of negative 1. You could also just flip it. Up to you how you do this. What you'll end up getting is you'll get about 0.01875. Now remember, this is in meters, and it looks like in part B they do stuff in centimeters, so let's just change it to centimeters. Might be a little easier. So move the dot 1, 2 over 1.875 centimeters. That's our A value. Now we want a B value, so B is equal to A over 2. This is for the TE10 mode. We get 1.875 centimeters divided by 2, and this is equal to 0.9375 centimeters. So what we're going to have is we're going to have a 1.75 centimeter by 0.9375 centimeter block. That's our waveguide, our rectangular, air-filled rectangular waveguide. So that's part A, not too bad. Part B, it says an air-filled rectangular waveguide has A, so now they're telling us what A and B are. A is equal to 2 centimeters, B is equal to 1 centimeter, and the frequency now is 5 gigahertz. It says find the attenuation, alpha, of the TE10 mode in dB after a distance of 10 centimeters. So Z is equal to 10 centimeters, or is equal to 0.1 meters. All right, so in the TE10 mode, alpha is a little different. It's not going to be your standard, K double prime times the depth of penetration times 8.686. This is a little different. What we have to do now is this is straight from the notes, by the way, and I don't believe this is in the formula sheet. I think in the formula sheet they have for the cutoff frequencies. But what you do is for alpha, you get pi over A squared minus K0 squared, K naught squared. So we know pi, constant. We know A to be 2 centimeters. And we know K naught. K naught is something we don't know, but all it is omega times mu naught times epsilon naught. It can also be rewritten as 2 pi over lambda 0, which lambda 0 is C over F. So this is 2 pi F over C. Either way you do this, mu naught is 4 pi times 10 to the minus 7. This is in the formula sheet. And epsilon naught is 8.85 times 10 to the minus 12. C is going to be 3 times 10 to the 8th. F is going to be the frequency, 5 times 10 to the 9. So what we get, when either way you do this, perfectly fine, what you get is 104.761. Plugging this into this equation, we get the square root of pi divided by 2 centimeters, which is 2 times 10 to the minus 2, or 0.02 squared, minus K0, which is 104.761 squared. And what we end up getting is 117.04 Nepers. Making sure it's not in Nepers per meter. Yes, it is. It is Nepers per meter. So that's our alpha value. All I did was plug in, plugged in my points here, got a value. I can check over it one more time because I did do it earlier today. So it could be wrong, although I don't think it is. 104.761. Yeah, 117.04. Okay, cool. So we get alpha is equal to that value, yeah. But we're not looking for alpha, we're looking for the attenuation. Now that might be a little confusing. Isn't alpha attenuation? Not exactly in this problem. What we have to do is we have to say attenuation is equal to alpha times, again, 8.686, because we want to get it in dBs. But remember, we want it in dBs, not dBs per meter, because if we did alpha times 8.686, all 8.686 does is change meters per meter to dB per meter. If we want to get rid of that per meter, we need to multiply by some meters, right? We want to get rid of, because 8.686 turns meters to dB. To get rid of meters in the denominator, we need to multiply by meters, and we're given a 10 centimeter, which is 0.1. And so what we do is we plug that in, 117.04 meters per meter times 0.1 meters times 8.686. And now what we get is 101.67 dB. Write it down here a little bigger. And that is our answer for the attenuation at 10 centimeters in the z direction. That's how you do this type of problem. I will say I'll actually go through 2022, which is, if you notice here, it's the exact same. Actually, on here, I think I did this one wrong for sure. Well, no, actually. No, I think I went back and changed it. Let me check. Yeah, I went back and changed this one. One of these I did it completely wrong because I just chose a random value, but no, I changed back. I went back here. This one is something that might be a little tricky because you have to do something in power. But the equation is straight from the formula sheet. Just plug it in and solve. But yeah, so hopefully this made sense. The past 3 years, they've been the exact same question. And with this rectangular waveguide, the 2009, 2012, and 2013, those are a little more tricky. I haven't seen one recently like those, but of course he could still put those on, so make sure you really understand this stuff. Hopefully this helped y'all though. If y'all have any questions, make sure to comment them or send me a message in Discord. But thank you for listening.